Welcome to the CAP seminar. It's my pleasure to introduce Nicholas Earl, and we're gonna have a double header today. So we're gonna have Bhaskar talk at 30 minutes, and Nick's gonna go first.
Okay, cool. Thanks for the introduction. As mentioned, I am a current CAPS fellow, and today I kind of want to give a project update. I know it's still a little bit early in the semester. I still got some time left, so don't pressure me too much. About a research topic that I proposed that is going to use a novel machine learning technique called neural processes to effectively identify tidal disruption events using their photometry. And so to begin this, I kind of want to just give the sort of rundown of what a tidal disruption event is. For those unfamiliar, it is an event that occurs when a star gets too close to a black hole and gets tidally disrupted by the gravitational force of the black hole, with its material then strewn around that eventually coalesces into an elliptical or circular accretion disk. And then as that material is deposited onto the black hole, we get this kind of bright flare of radiation that was initially predicted to occur in the X-ray. And so that's sort of what you see on the left here, just sort of in schematic view. And then the top right is some more recent adaptations of this conceptual picture that adds in the notion of viewer angle dependence on how you might see the radiation that's emitted from this event. And then in the bottom right is just a handful of tidal disruption events and their bolometric luminosities over time to kind of give you an idea of some of the characteristics that we generally look for tidal disruption events. Some type of rise, a peak, around 10 to the 44 ergs per second, and a characteristic decline from that peak are generally what we see. Now the problem is that although this original conceptual model has been great at identifying some TDEs, it does not fit all of the TDEs that we see. And in fact, most recent TDEs have been identified in the UV optical and not the X-ray. And so to sort of remedy this situation, we've come up with this notion that there is a cloud of material that forms around the disk that we call the reprocessing layer that acts to reprocess the X-ray from the high energy to lower energy UV optical data. Recent magnetohydrodynamic simulations have found that this reprocessing layer can have an accretion rate dependence such that as your accretion rate decreases, as the material being deposited on the black hole slows down, the reprocessing layer becomes more transparent and more X-rays can be emitted. What this means is that we might see a very strong UV optical peak with no initial X-ray, but get an X-ray brightening at later times. And so this is not obviously the only interpretation of our data, right? So this viewing angle dependence I mentioned earlier, still does propose that we can find TDEs based solely on their X-ray, and we do. It just happens to be that it's not the most prominent aspect of TDEs of the ones that we have found. However, this notion of accretion onto a black hole has not been able to fit all of the TDEs that we've come across. And so more models have been proposed to kind of understand these sort of more errant TDEs that we find in our observations. So on the right here is a different model where the primary UV optical peak does not come from the accretion behavior of the material from the disk onto the black hole. Instead, it comes from the shocks created in the collisions of the debris streams as they circularize. So this event happens further away from the nucleus of the galaxy generally than the accretion model, and has different predictions for what you might see, although the behavior of the light curve over time is meant to be quite similar. We may never see some coincident X-ray emission. Likewise, we may see different outflow behavior, especially in the spectra. But this, of course, gives just another view on the possible models that could represent the actual physical happenings of a tidal disruption event. All this to say that our current understanding of TDEs is myriad. There is not a single sort of unified model for really understanding the source of radiation from a tidal disruption event, and that has led to quite a few problems, especially because we are on the clock right now. We really need a way to kind of solidify our ability to identify tidal disruption events, especially photometrically. Currently, we see maybe a dozen or so a year. Our current sort of corpus of TDEs numbers roughly about 100, which is not great. And in the era of Vera Rubin, the optimistic estimates place about a couple thousand of TDEs possibly occurring every year. And so as sort of Nick Stone kind of highlights in his most recent book, which is on the archive, so I encourage you to look at it, this sort of classical semi-empirical criteria that we established currently for TDEs is really only good at capturing about 10% of all the TDEs that might be happening every year. And so this really kind of highlights the need for finding sort of a deterministic model for really truly identifying something as a tidal disruption event. On the right here is just sort of some estimates from a relatively recent paper about the number of TDEs that are proposed to be seen over the next 10 years through Vera Rubin, given different sort of mass distribution functions for the central supermassive black hole. And they number anywhere from about 30,000 to all the way up to 80,000. So we're kind of on the clock to kind of find a nice way to figure out whether a transient is a TDE so we don't miss out on all these wonderful events that are going to be happening in the near future. So to my proposal, right? So my proposal kind of posits the question, is there some sort of machine learning model that we can use that, given a series of initial observations of a potential transient, could then produce a prediction of what the light curve might look like, and then from that light curve, identify whether or not, or give a confidence interval about whether or not that object might or might not be a TDE. And so to do that,
So maybe you'll talk about this later, but if I remember correctly. So maybe you talk about this later, but if I remember correctly, Patrick Aleo wrote a similar model for supernova classification. Can you talk a bit more about what he did for supernova and how that compares to what you're trying to do for TDEs?
Yeah, I'll talk about that at the end. I do have a slide for that. This is not a particularly novel idea, although the implementation is what makes it unique, right? So as kind of pointed out by Akshat, this sort of notion of taking photometric observations and making predictions using a machine learning model is not new. But what is new about this is to take a particular approach using what are called neural processes. Now, most people in the machine learning community are familiar with neural networks and Gaussian processes. Neural processes are a way to try to take the best parts of neural networks and the best part of Gaussian processes and merge them together. So neural networks are excellent, but they work extremely well only when you have huge amounts of data. As I mentioned, our body of TDEs, our well-identified TDEs, only numbers about 100. So that doesn't work well for the context of neural networks. Likewise, in your typical neural network implementation, you generally only get a mean prediction. You don't get sort of your uncertainty estimates for those predictions. And that's sort of where Gaussian processes come in. Gaussian processes are really great about creating distributions over functions. They're really great for inference, Bayesian inference, and they give sort of a mean and error estimate on your predictions, which are great. However, Gaussian processes require fine-tuning of the sort of kernel function internally, which does require some notion of the underlying model, which would, for our instances, describe tidal disruption events. And as I've mentioned, we don't really have a great one. In addition to that, Gaussian processes are much more inefficient as your number of data grows. So as your number of observations grows, they become more efficient. They scale cubically as opposed to linearly. And so in the potential future, where we have lots of potential data, they may fail to perform efficiently. And neural processes are a way to sort of remedy this. They are, like Gaussian processes, a probabilistic model. They are few-shot learners, which means that you can get sort of convergent predictions with just a few examples or a small amount of data. And it is part of a machine learning family called meta-learners, which mean that they actively improve over time. They quote-unquote learn to learn. And this is particularly great as we expect to be subsuming a lot more photometric data from tidal disruption events identified in the era of Vera Rubin and these other sky surveys. So being able to immediately incorporate that information into the model without having to completely retrain it is a huge, huge plus. So this is just a quick overview of what a conditional neural process is. So we have an unknown blue function and observations of that function, which are given by our x1s and our y1s there. And we want to make a prediction at time xt. So what we do is we take each of our observations for this particular unknown function, use an encoder to create a local representation space, combine those or aggregate those representation spaces into a global representation space, combine that global representation space with our target time, pass it through a decoder to get a mean and variance for our prediction. And now what's nice, because it does sort of take this probabilistic approach, we can feed it variations of a function or different data sets and basically continually add to this neural process model over time. This is sort of a laid out overview comparing sort of your typical supervised learning neural network on the right, where you effectively take in a huge amount of data, you train a model, G, you use that model, give it input times to make predictions at those times. And in the bottom, we have sort of the the neural process approach, where it is not a single set of a huge amount of data, but rather smaller sets of data or sets of data. Each of those are sort of encoded into their local parameter, their local representation space, aggregated, and then that aggregation, the aggregated representation space is used to make predictions. And that aggregation method is generally sort of order invariant in the sense that it could be a mean or a sum, which means that we can continually add to this aggregated representation space over time without having to start all over from the beginning. So this is just a bit of an overview of where neural processes kind of fit into the machine learning family. So on the left, you have your sort of supervised learning methods, your neural networks that take your data and attempt to figure out or train a model that can predict, that can approximate the underlying function. You have your stochastic processes and your Gaussian processes, which take that data and attempt to form a probability or a distribution over potential functions that can fit your data. And then on the right, we have this sort of this meta-learning family where we feed it in during training sort of this number of tasks, and the meta-learning algorithm kind of learns sort of the underlying family of functions that can describe each task, and then can adapt at test time to whatever task it needs to perform. And neural processes is sort of the analog to Gaussian processes in this case, where we're generating sort of a probability distribution from this underlying function or family of functions. Okay, so back to my project. Yeah, go ahead.
So Nick, in addition to the intrinsic variability of TDEs, you of course got extrinsic effects where there are different redshifts, they have different reddening. How do you prevent the neural process from learning about redshift when what you actually care about is make predictions for this TDE in, say, the rest frame or something?
Yeah, and that's a very good question. That's not something I've quite tackled yet. My notion is that, the most obvious thing is to get some maybe photometric estimate of the redshift and basically de-redshift the object, and then use the de-redshifted photometric data to train the model. And that way we can be agnostic of sort of the distance to the object. Other things is that we can just treat redshift as another parameter in the model. That is certainly possible as well. However, that would take some measure of performance estimates to see how well the model can incorporate that data and still make reasonable predictions, especially in the face of imposter objects like flaring AGN or particular types of supernovae. Right? So that is certainly a task for later.
So, okay, it worked. I'm going to ask a very naive question, and probably embarrassingly naive considering how many times you've explained how this works to me. But so you've talked about how neural processes combine some of the best attributes of neural networks and then also Gaussian processes. I'm wondering what the downside is in terms of, why not now use neural processes anytime you would previously use a Gaussian process or a neural network?
Yeah, so there are certainly downsides to neural processes. The most obvious one is that it is much more complex than your typical neural network. It has much more, although you don't particularly care about the range of parameters that it's attempting to approximate, you do still have to care about the dimensionality of your latent space, the transformation from the representation spaces into real space, and sort of fine-tuning those aspects of the neural process can be tricky in its own right. So if, generally if you have a ton of data, it's best just to use a neural network. If you have a really good idea of what the underlying function is and you can make a great approximation using, some implicit kernel function or explicit kernel function, it might be best to use Gaussian processes.
So do I take your meaning that when we have a ton of TDEs, it might be worth it to switch to using a neural network?
Yeah.
Okay.
I will state, though, that you still gain the benefits of a neural network at the neural process that although neural processes can be fundamentally used for few-shot learning, meaning it only needs a handful of data to make predictions. Because it's parameterizing based on the neural network, its performance still scales well with the number of observations that you have, right? So you can still get that benefit even with neural processes. Okay, so my project can be sort of loosely broken up into 3 phases. The first one is to effectively put together a neural process model or a set of neural process models. Neural processes have not been really sort of used often in astronomy, particularly. The context is generally geophysics or biomedical situations currently. So there isn't a lot of examples to go off of. And then I needed to kind of generate some type of estimate of the performance of the model using some kind of simplified model data, right? So I created a simplified TDE model that I can use to loosely train the neural process model and kind of get an idea of its performance and sort of the range of the hyperparameter estimation that we can incorporate into the model. So the first thing I did was kind of piece together a simplified TDE model. There's many of these in the literature. The typical ones are basically assuming a Gaussian rise and a power law fallback. The other one is basically just putting two power laws together, which is sort of the approach that I took, which gave me some, a loose estimate of what a TDE might or might not look like. And then I decided to adopt PyTorch as sort of the underlying machine learning framework to use in this case. In PyTorch, you can kind of teach it to create, design a generator to produce a bunch of potential data to train on. And that's just sort of what I'm showing here with particular parameter ranges for my TDE model. It just asked it to generate varying samples of the TDE model, varying amounts of the samples of the TDE model. Yeah, go ahead.
On the power and the power law, is that based on physics or is that just?
Well, so the fallback is based on physics, assuming the mass accretion rate onto the black hole. The sort of t to the minus 5/3 does have its origins in sort of the accretion disk process and how the matter is accreted. The rise time is less uncertain. There isn't a clear indication that there is sort of a physical model for why the rise time has the shape it does, which is why it can either take power law form or Gaussian form, and it sort of varies with the composition of the star, the size of your black hole, the spin of your black hole. So there isn't a clear, obvious understanding source for the rise.
So I'm curious to know what coefficients are changing to produce the different models on the right plot, and why do you need PyTorch to do something like that?
Yeah, so I'll start with your second question. So PyTorch is great because it really gives a great way to kind of move things to the GPU for efficient modeling and training of your model. And it just happens to have these really nicely incorporated tools for generating example data. And so that's sort of just what I'm demonstrating here. The variables that are changing in this are basically the power law indexes for the rise time and the fallback time, the sort of smoothing parameter between the two power laws, which can dictate the width of the peak, which has been associated towards the for instance, the viscosity behavior in the accretion disk in the fallback rate of the TDE. And let me think. And then the amplitude of the power laws. So it's quite simple.
So yeah, one quick follow-up on that. If one of the parameters that you're changing is the power law itself, does that not make it less physical? If the two power laws that are shown on your left plot, if they're physically motivated, and then to generate the various light curves on the right, if one of the things that you're changing is that power law, does that not make your curves on the right less physically motivated?
So the range of parameters for our power law index are physically motivated, right? So we have estimates of the behavior, for instance, for a partial disruption event, which has a steeper fallback, all the way up to just sort of regular disk emission from an accretion disk around a black hole. And so that kind of bounds our expected behavior of the fallback rate.
I understand. Okay, thanks.
Okay, so I combed through all the literature. I took all the pieces, sort of painstakingly composed it in PyTorch, and constructed the encoder and the decoder and the latent space variables, set up my layers, and sort of ran through some test data. So on the left here, it was my initial test, which is effectively just taking random observations of a tidal disruption event and seeing how well the model can adapt to just a random set of observations that we might get over a series of nightly observations, for instance. Of course, this is not realistic. We wouldn't expect it to work this way, but I wanted to see how well the model might adapt to the data. It is a little slower than I hoped, and this is a limitation to my training regime, where I had been trying to get this up on the campus cluster using the GPUs there, struggled with it, ended up kind of pulling it down and running it locally or on sort of a Google Cloud cluster that was already pre-built for this particular machine learning context, and then ran out of GPU credits. So this is a bit truncated, but you can see that it more or less responds well to the data. It is a bit slow, which is a bit concerning, and it may be an issue with my how many iterations I put in, for instance, for the training. But I was loosely heartened that my bespoke model kind of worked as well as it did. So then I tried basically doing a sequential observation test, which in this case mimics what you might see from an observatory, taking nightly observations, accumulating it over time. And unfortunately, I didn't see as great of a response as I was hoping. So eventually, the model does converge on the observations. However, it does so on a timescale that's not particularly useful for our use case. And so this was a big concern of mine, and I thought about this for a while. I went back to the papers, eventually reached out to one of the authors, Wessel Bruinsma, who is a senior researcher at the AI for Science Initiative at Microsoft Research in Amsterdam, and asked him, here's my context for wanting to use neural processes. Can you make recommendations about, is it perhaps a misunderstanding of the dimensionality of my latent space, or do I need more iterations? And sort of the first thing he kind of came back and told me was, well, why don't you try using an attentive conditional neural process? And this way you kind of incorporate an attention mechanism into the model, which basically allows it to weight different points differently over the course of your input observations. And what this means is that the model can learn that perhaps observations near the initial part of the rise time of our TDE are more important than some random one that's in the middle of the rise time, or that observations near the peak should be weighted more important than some that are maybe in the middle of the fallback. The other thing he told me was that he actually has built a framework in Python for building neural processes. No more do I need to kind of build all the pieces individually using sort of the low-level PyTorch models. I can instead adapt his building blocks from the framework that he used. And so that was great. I took this approach. I ended up kind of building up this attentive conditional neural process, and was able to get something that was much closer to what I wanted, right? So in this case, the dark blue points are sort of the simulated nightly observations, and the unfilled points are sort of the ground truth of our underlying model, and then of course we have the mean invariance of our neural process that gives us a prediction of our light curve. Now this was much closer to what I wanted, much better, and kind of gave me confidence going forward. He also mentioned that there is an even more sophisticated model called a recurrent attentive conditional neural process, which is even, if you're familiar with recurrent neural networks, is even better at incorporating time series data. I have yet to implement this particular model, but definitely plan to do so. So thanks, Wessel. Okay, so now I've moved on to effectively phase 2, where the primary thing that I would like to do is transition to a more physically based modeling system by incorporating more sophisticated packages like MOSFET, which takes this, it takes the accretion sort of model approach to tidal disruption events based on simulations to generate predictions at particular observation times, and then use that to kind of create my sample set of data. And that way I can still implicitly understand all the pieces that are going into the data and how they might relate to the predictions from the model. The second thing is sort of the capstone to this project, which is how do we get an estimate of the prediction out of our generated light curves. And so in this phase 2, I'll be incorporating additional channels into the neural network architecture that will allow it to train on sort of this classification scheme and give sort of a confidence interval for the prediction of whether or not it is a TDE. Now, in lieu of that, one thing we could do is use, as Akshat pointed out, there is sort of a set of neural networks that are already pre-trained that attempt to do this sort of prediction given photometric data. We could use the neural process model to generate light curve predictions of newly identified transients and feed those predictions to the pre-existing neural network model and see what that says. Ideally, I would like to compare these two approaches to see how well our inbuilt neural process model is at classifying a potential TDE versus sort of a post-regression classification of the light curve. And then, of course, this will also involve more fine-tuning of the latent dimensions, of the latent space, of the learning rate, things like that. And then finally, I will be composing a complete set of the current TDEs in the literature, and then using that to train my neural process model. And of course, I will be working on comparing these individual neural process models and classification schemes to see how well they perform against each other. So that sort of ends the talk. There is a slide here, Akshat, about comparison to previous neural networks if you want to have a sort of discussion after this about it. But with that, I'll just say thanks for joining, and here are my references.
Why did you elect to do all of this in bolometric luminosity space rather than just in the observed bands?
Yeah, so fundamentally, it doesn't quite matter because the data gets normalized before it gets trained at this moment. The reason why I chose luminosity is that there's a much cleaner sort of analytical approach to understanding the luminosity behavior versus, for instance, the magnitude behavior of the data. The reason I chose bolometric is because one thing is easier than 5 or 6 things. But indeed, I do want to transition to using individual bands, especially those that are analogous to the LSST bands specifically, right?
Good afternoon, everyone. My name is Bhaskar. I am a CAPS fellow, and I'm a graduate student in the Department of Aerospace Engineering. Today, now we're going to look a little bit closer home, and we're going to explore the solar system in millimeter wavelengths using CMB observations that we already have. First of all, why study asteroids? One-word answer would be curiosity. But then asteroids are debris that remain here from the beginning of the solar system. So they can actually give us clues to how the solar system would have been in that time, clues about how the chemical and physical conditions were at Earth in the beginning of the solar system. although we haven't seen life anywhere outside the Earth in the solar system, it's possible that the asteroids brought life in here too. And then there are also a rich supply of minerals, and I guess sometime soon we'll be going on for mining them. Asteroids have generally been observed in IR and optical wavelengths, but people haven't looked at them in millimeter waves that much. The flux that we see in IR and optical, it constitutes of both the reflected solar radiation and the thermal radiation from the asteroids. But you can see that even at 10 microns, the reflected solar radiation goes down, and it's mostly the thermal radiation coming from those asteroids. So at millimeter wavelengths, it's almost exclusively the emission from that asteroid. And more interestingly, it is not just emission from the surface, it is also emission from the subsurface layers. So if we can properly understand the data, analyze the data that we get in millimeter waves, it can give us it can tell us things about the surface and also subsurface conditions of asteroids. And it can also be potentially used for a better classification of the asteroids than the classification system we already have. All of that is there, but there's a problem. So people have been observing asteroids in millimeter wavelengths since like 1982. And consistently, they have seen that in millimeter wavelengths, the flux that people observe are lower than the expected flux. Expected flux means you see it in IR, and then you get the brightness temperature, and you expect a certain amount of flux due to that temperature at millimeter waves. So in microwave, Johnston et al. Saw Ceres, and the brightness temperature that they get from the microwave observations is 120 Kelvin, while the expected temperature was 165. There's a gap. It was early, and they say that maybe the diameter is incorrect, maybe the rotational axis is not right, and a lot of things. But they also noted that even then, other people have been noticing that anomaly. There are some other works that have noted the same thing. And even till 2023, people are seeing that there is a deficit in flux for asteroids. This plot basically shows different classes of asteroids, and the percentage difference in the flux is nothing but, so you see that asteroid with WISE data, you get the flux, and then you get an expected flux in the microwave, and then you compare it with the observed, and almost always there is a deficit. Sometimes going to like 40% and stuff. So we don't understand this. It's a problem, but it's also an opportunity for, because something is happening, some physical process or something is happening that's causing the asteroid to emit less flux than there is. Historically, people would think that this is due to a reduced effective emissivity at those higher wavelengths. That might be just a modeling parameter, but what people would say is that maybe there is scattering below the surface, which is not allowing the radiation to effectively come out from below the surface, since a lot of the radiation comes from the subsurface. Also, the flux predictions are generally based upon much simpler models like NEATM. They do not consider the shape of the asteroid, how it rotates, and also the subsurface conditions. It takes the surface temperature and it just predicts the flux. But again, in 2013 and around that time, people started saying that maybe it is because of a sharp temperature gradient below the surface. The surface is hot, but there's no atmosphere, and whenever it goes to the night side, it radiates like desert, and it becomes cold, and the subsurface is cold. So maybe because the subsurface is actually cold and a lot of the radiation comes from down there, it's causing the deficit. So we wanted to investigate what's going on to begin with. So yeah, that's our objective. First, we want to understand why is there the discrepancy between the predicted and the observed flux in the millimeter. What's happening? Once we understand, we will develop the ability to predict the flux at those millimeter wavelengths. And then CMB-S4 is coming in a few years. We want to predict the observability and discoverability, whatever it can do in terms of solar system objects, like how many asteroids is it going to see, what is it going to see, and can it also detect new asteroids and maybe comets. That's all it is. And also explore what new physics we can get from there. So we have a thermophysical model that, yes?
Sorry, so if you go back to your previous slide, I'm assuming that the problem of figuring out the discrepancy in the two temperatures and the prospect of CMB-S4 in terms of discoverability of solar system objects, those are two separate problems, is that right?
Yes, they are, okay. But I'm keeping them one after the other because if we don't understand why is there the flux deficit, we won't be able to properly predict how things are going to look. So maybe something, the predicted flux says, okay, you can observe this, but actually the flux is much lower and you cannot even see that thing. So that's a problem.
I understand the connection now, I think. Thanks.
So we have a thermophysical model that can simulate asteroid temperatures throughout the body, not just on the surface. And for that, it accepts a shape model for the asteroid. So if we have enough data, like radar shape model thing, the shape model would be like a triangulated surface mesh as like objects in a computer game. And then we've also made some additions to it so that it can take in JPL horizons ephemeris data. So we know exactly where the asteroid is at a certain time when an observation is taken. Along with the shape model, if we get the proper spin orientation of the asteroid, so now we have the asteroid, we have its spin orientation, we know the rotation period and everything, and we also know how it is positioned with respect to the sun. So we can get the exact orientation of that asteroid in space when we observe it from Earth. So in that way, we can get the exact orientation of the asteroid. We have proper surface and subsurface temperature modeled. So this gives us a tool to investigate whether subsurface temperature is actually causing this drop in flux. And so this is how asteroid Calliope looks from one of our simulations when we ran it with a thermal inertia of 200. That's in SI units, TIU. Thermal inertia, as the name suggests, is the inertia of a body to resist change in temperature. A higher thermal inertia would mean that the asteroid doesn't want to heat up easily, and it won't also cool down easily. A lower thermal inertia will be the opposite. This thing, the spin axis is like this. It's spinning over there, but as you can see, the top surface is hot and this is cold. This thing is, by the way, frozen in time. I'm just rotating it to show all the sides. The way asteroid Calliope is oriented is that side is always facing the sun during the time that we have been observing it. So that's why it looks like this. And yes? Yeah, I'm done actually.
How is thermal inertia different than capacity?
It also takes in heat capacity, conductivity, and the density. So it's root over K, rho, Cp. That's the thermal inertia. It's a composite of those.
And then you made this model?
Yeah. No, the shape is available, and the temperature values, that's what we have obtained.
Got it. Okay, so this is, okay, I think that answers. So this is effectively an arbitrary line.
No. This is actually how Calliope looks, but I have overlaid the temperature on top of it.
But I mean, is this a real asteroid in the sky, or this is just one that somebody?
No, it's a real asteroid in the sky.
Okay.
Mm-hmm. So using radar, people figure out how the asteroid would shape it would be, and then how the spin orientation. I've just used that data from. If they're large enough, like this is, I guess, 160, 170 kilometers diameter. If they're large enough, we get good enough models. I've shown asteroid Bennu here. Yeah, we also have a very good shape model for that, but that's because the Sirius-X visited it. Yeah. Yeah. Okay. Then let's come to what we observe. Okay. Now, here we compare how the flux from our simulations look in contrast with actual observations. The gray, the dots with the lines are observations of asteroid Calliope, which was published in Paul's paper. And okay, there's a lot of stuff here. The blue line is a naive, just a quadratic fit to this data. You can see 3 things over there, SIM TI 300, TI 200, and TI 100. Those are our simulations that we ran at 3 different thermal inertias, 300, 200, and 100. The 100 being more susceptible to change in temperatures. But you don't see all those lines over there. You just see a red line, I guess. That's because what happened is even if we change the thermal inertia in this case, there was a very small and negligible change in the temperature. Because as you can see here, the side facing the sun is always facing the sun during those few months of our simulation. So one thing I noticed is when I change the thermal inertia, when I reduce the thermal inertia, the night side is getting much colder because it's radiating heat easily, but the day side it's exposed and it is getting as hot as it can be. So it kind of remains there. And the dotted line is from the Needham prediction of the flux. That should be there. Apparently, everything looks good and all of them are close. There are a few problems, though, here. First of all, the error bars are too high for our purposes. We would, like, from this data, I think it's difficult to say what the actual flux should be. And also, there are some highly negative values, which they are below 0, even considering the error, they don't go above 0. So I don't know why. I don't know what is going on there. Like an asteroid can't have a negative flux, but yeah, probably. But there are a lot of negative values. But anyway, the observations and the like the fit to the observation and the simulations look close, but not really. So if we zoom into the first part and have a look there, again, even with our model, which has subsurface temperature, which has the proper shape of the asteroid, proper spin, and proper orientation, we get around 37% higher flux at that region, and it's mostly the same throughout. It's also seen that our simulation results are closer to Needham, which is a much simpler model, but should be then use Needham. Yeah. The asteroid is rotating. So I'll show in the next slide. The shape really changes depending on where you see it from and all of that. So that's causing those small bumps. And so yeah, yes.
Yeah. Do you have to make an assumption on like the composition of the asteroid to get like a measure of albedo or something?
This one is an M-type asteroid, so it's mostly metallic. Based on that, we can make some assumptions. Like how much the specific heat would be and the thermal inertia and all those stuff. But as you can see, because of how this thing is rotating, thermal inertia is almost having no effect on the temperature profiles. So although Needham is very close to our simulations in this case, it may not be in other cases, because the way Needham works is it will either consider the asteroid to be a slow rotator where that one side is always facing the sun, it gets hot, and and the sides are relatively colder, and it goes to the night side, or it considers the asteroid to be a fast rotator where the temperature just equilibrates everywhere. Fun thing in case of this asteroid, that thing is actually favored because that same side looks towards the sun for a long time, for a few months. But then it doesn't consider the shape of the asteroid. As you can see, I've shown it from various angles. This thing will take in a diameter value for the asteroid because it's a sphere, but the projected area will be really different if you look at it from different angles, and also the temperature distribution depending on where we look at it from. So it's really important to have a better model like this and get a deeper insight. But yes, it is seemingly not solving the higher flux that we observe over here. So we again look at what are the other possibilities. This paper in 2021, they were saying that M-type asteroids like Calliope have been assigned low thermal inertias, but they say that the thermal inertia should actually be higher. It is, yes?
So I think I'm having a bit of trouble connecting what you presented earlier and what you presented later. If I remember correctly, one of the main motivations for going to millimeter was to be able to probe subsurface physics. That was something that was not possible with infrared or optical. And I'm curious to know, the analysis that you've done so far, is there something that you've learned about subsurface physics that has not been possible previously with optical or IR?
Oh, sure. I'm sorry. I think I didn't explain it. So the fluxes that we obtained from our simulations, it already considers the subsurface temperatures.
Okay.
Yes.
Okay.
But even with that, we are not getting there. We're not getting where we should be. So yes, I think this might be a good sign. There might be scattering below the surface and a lot of other stuffs that we are right now exploring. And that's the subsurface physics that I'm talking about, that we can understand from solving this discrepancy.
Okay. I understand now. Thanks.
Okay. So these people, they analyzed Psyche, and they noted that the thermal emission that they observed is mostly unpolarized, and that surface roughness alone cannot get rid of the polarization. So now again, they are suspecting that maybe there is scattering below the surface by micron-sized particles, metallic particles, which are removing the polarization. In the beginning, I said that people attributed the dip in flux to a lower effective emissivity, which is caused by scattering. And then we went back to maybe subsurface temperature is causing it, but then people are again back to probably scattering. Now, with our model, we see that subsurface temperature dip is not the only reason. So again, we are going to look at whether scattering is the culprit here. But there is more work to be done to properly understand what is causing that. Once that gap is filled, I think we can more accurately predict the temperatures. And we are going to use the SORCA solar system survey simulator, which is being developed. It is mainly being developed to be worked on the Rubin Observatory, but we can also use it for CMB-S4. And then, yeah. Oh, I didn't complete. I didn't complete the sentence over there. I'm sorry. Yes. So CMB-S4 survey simulation with SORCA will then give us an idea about what we can see with CMB-S4 with regard in the context of solar system objects. And we will also explore if we can do machine learning to speed up the whole process. Once we have done analysis on a lot of asteroids, maybe we have enough data to, without even running the simulation, we can kind of say what's going on. Yeah, that's all I had. Here are my references and yes. Oh. Yes.
Forgive me if this is a very naive question. What does Scorcha do?
Oh, it's a survey simulator. So if you give it which part of the sky this thing is going to, this observation, this project is going to look at, and what is the capability of that telescope, how much it can see, it will tell you what are the objects it will see and in how much detail and all of that. Broadly. Oh,
so is the point that because I look at things outside of the solar system, so I guess this wasn't intuitive. Is it because things in the solar system move on the sky?
Yeah.
Okay.
Thank you for the talk. Really cool. One thing I wanted to ask about your temperature models is how sensitive are they to the composition of the asteroids?
These things. Well, we do not put in anything directly with respect to the composition, but yes, sometimes from all the simulations that I have run, I don't see them to be too much sensitive unless there is a lot of difference in the compositions. Yeah. Even specific heat, which is something that we have fixed in our case, like 500 or something. They don't remain fixed with temperature. So, in an ideal case, we would have to have an equation that will say whatever the temperature is at whatever point, use that specific heat and things like that. But yes, more or less they work. Yes.
Very similar question to David's question is that how much of emissivity change based on the composition of this asteroid? Because when you convert the temperature to the flux, you need that emissivity. And how good of a measurement do we have on the asteroid's emissivity?
Mostly asteroids have been shown to give emissivities like from 0.9 to 1 and in that range, so it's not really very different. But in some cases, like in larger wavelengths, people say that the emissivities drop to like 0.6, 7. But yeah, we don't actually know if this is because of the drop in emissivity or something else. So it's somewhat still a mystery. But yes.
You talk about how you would like to discover new asteroids with CMB-S4. Do you think that the current cadence of CMB-S4 will be sufficient enough to discover, I guess, new asteroids, or will it, just streak across the image because your timing is not enough?
Not sure. If they're large enough, maybe they're already discovered. But it's possible that if what I think is if we have a better way of analyzing the data, we might be able to get, if we can reduce the noise even more and do stuff like that, maybe you can see something. I'm not sure.
Okay. Thank you.
Is totally left field. Is it generic when I imagine weird shaped asteroids out there? I imagine them sort of tumbling, right? Is it generic that they settle down into some sort of a nice stately rotation about one axis, kind of facing the sun? Is that a
no? Not always.
Okay.
Not always. But then I got this shape model from the Dammit website, and they kind of simplified the process and gave a single spin axis. But yeah, we might be also able to simulate the tumbling if we want to.
Yeah, and related to that question, so when you take shape models from radar, you only get two spatial axes, and the third axis is actually velocity, of course. And so there has to be some assumption in going from velocity to a three-dimensional shape. What are the errors on this, maybe for Calliope, because it's so large, it's small, but for something like Bennu, they should be completely settled, since we have shapes from actually visiting the asteroid. And do those uncertainties on shape give you enough leeway to put an error bar around your model such that it becomes more consistent with the data?
So yeah, as you were saying, like this shape model, it has, I think, 2,000 something triangles on the surface. Whereas for Bennu, I think we have like 20,000, even if it's a few 100-meter size asteroid. But I still think that it's an improvement, considering that we used to just consider them as spheres. There might be some errors, but I think even with this level of shape model, the result should be quite good. Yeah, specifically if we. So here I have considered isotropic emission from all the surfaces. So if we even divide the surface into multiple fragments and have them in more angled orientations everywhere, ultimately if that surface area is the same, then I get a similar amount of radiation to